force on M1 is T1 minus 3.92. Now remember, we are only considering the magnitudes here. So T1 minus 3.92 is the net force on M1. Now, if F net is the net force on M1, we would say F net equal to MA. Is that right? F net equal to MA, or T1 minus 3.92 Newton equal to M1A. M1 is 0.4 kilogram times A. Now we have an equation that contains two unknowns, T1 and A. We can obtain a similar equation by taking the motion of M2. Well, I'm sure you can do this now on your own. What are the forces acting on M2? Its weight will be M2G, 0.8 kilogram times 9.8 meters squared. That is 7.84 Newton acting vertically down. So the weight of mg is 7.84 acting vertically down. What is the tension on the string? The tension on the string, we said earlier, that is T2. T2 acts vertically up. There you are. So what is the net force on the mass M2? Since the mass M2 is moving down, we would say the magnitude of the net force is 7.84 Newton minus T2. So this is the net force, 7.84 Newton minus T2. And this net force produces an acceleration on M2 such that net force F net equal to MA. The net force equal to M2 times A, 7.84 Newton minus T2 equal to 0.8 A. Now, do you agree with me that acceleration of these two, both the masses are the same? Yes, they are. It cannot be different because they are connected. If one is accelerating, the other also has the same acceleration. So, we have now a second equation, 7.84 Newton minus T2 equal to 0.8A, and the variables here are A and T2. The first equation, we have the variables A and T1. So, we have two equations and three unknowns, T1, T2, and A. We cannot solve these equations. We need to get a third equation. Where is the third equation going to come from? It's going to come from the rotation of the pulley. Alright, can you tell me, what is the net torque that rotates the pulley? The net torque. When you consider the rotation of the pulley, you must understand this T2 will be pulling this pulley on the side. T2 will be pulling it down here, and T1 will be pulling it down on the other side. Therefore, the net external force applying a torque will be T2 minus T1. And that external force multiply the radius of the disc will give you the net external torque. Okay. Now, let's consider the forces acting on the pulley. T1 tends to rotate the pulley clockwise. You understand that? This T1 will be trying to rotate the pulley clockwise, whereas T2 will be rotating the pulley in the counterclockwise direction. There you are. T1 rotates the pulley in the clockwise direction, and T2 will then rotate the pulley in the counterclockwise direction. The net force on the pulley, therefore, is T2 minus T1. And the net force will be acting down here. And what is the distance of that force from the axis of rotation? It is the radius of the pulley. Therefore, the external torque will be the net external force multiplied by that radius. This net force produces an external torque on the pulley given by tau external is T2 minus T1 times the radius of the pulley. This is the external torque. Now here, R is the radius of the pulley, which is 0.15 meter. Therefore, I can now say tau external is 0.15 times T2 minus T1. And the frictional torque, tau friction, we know that. Tau friction is 0.35 meter Newton, will oppose the external torque. So, if the external torque is trying to rotate the pulley in the counterclockwise direction, the frictional torque will be acting in the opposite direction. What is therefore the net torque on the pulley? The net torque, tau net, is external torque minus the frictional torque, because the frictional torque always opposes motion. That is, now this is the external torque in the counterclockwise direction, and this is the frictional torque in the opposite direction. The net torque will be the external torque minus the frictional torque. Alright, tell me what did we get as the external torque? Is T2 minus T1 times 0.15. So T2 minus T1 times 0.15 is the external torque, minus the frictional torque is 0.35. So this is the net torque on the pulley. And now you tell me, what does the net torque do on the pulley? The net torque will produce an angular acceleration on the pulley, given by the equation tau net equal to I alpha. Since the angular acceleration alpha of the pulley is caused by this net torque, we can say this tau net equal to I alpha. This net torque will be equal to I alpha. So I can now take this quantity. Well, do we know I? I is the moment of inertia of the pulley, and the pulley is the disc. What is the moment of inertia of a disc? Is 1/2 mr squared. Do we know these values? I equal to 1/2 mr squared. We know the mass, we know the radius, therefore you have mass is 0.2 kilogram, the radius is 0.15 meter, so the moment of inertia of the disc is 0.00225 kilogram meter square. So we have tau net is this quantity, I we know, and alpha is the angular acceleration. And you know that A equal to R alpha, isn't it? A point on the disk will have a tangential acceleration A, which is equal to R times the angular acceleration. Therefore, we can now find alpha in terms of A. So what we're going to do is, we are going to eliminate alpha and write that in terms of A. So alpha equal to A over R, and that will be A over 0.15. And that will be A over 0.15 is 6.75 A. I want you to watch how I replace this alpha in terms of A, the linear acceleration. Why is it necessary? Because the two equations we have developed so far are equations that contain T1, T2 and A. Now, we cannot have a third equation that contains yet another variable alpha. We need to express that alpha in terms of a, and that's what I'm doing here. So how did I do that? I know that a, the linear acceleration, equal to radius times the angular acceleration. Therefore alpha equal to a over r. That will be a over, the radius is 0.15 meter. That is 6.7 a. And look at this. I have the value of I is 0.00225 kilogram meter squared, and alpha equal to 6.7 a. Therefore, what is net torque? Equal to I alpha. I is 0.00225 kilogram meter squared, and alpha equal to 6.7 a. And that is 0.015 a. So tau net is 0.015 a, and therefore this quantity can be equated to this quantity, which is tau net. Okay, so we will now take this quantity and equate it to 0.015 a to produce a third equation on T1, T2 and A. Let's do that. So we will now have 0.015 A equal to 0.15 times T2 minus T1 minus 0.35. Let's simplify that equation. Rearranging this will give me this. Now distribute 0.15 and rearrange it. It will become 0.15 T1 minus 0.15 T2 plus 0.015 A equal to negative 0.35. You have now three equations and three variables, and you know how to make a matrix, how to make matrices and solve them. Rearrange those three equations. Look at the way I'm writing them. T1 plus 0 T2 minus 0.4A equal to 3.92. That is our first equation, this equation. And the second equation is 0 T1 plus T2 plus 0.8A is 7.84, rearranging this equation. We are aligning T1, T2 and A on the left side and writing the constant numbers on the right side. And now you have equations 1, 2 and 3. Okay, I want you to make a matrix using these coefficients. It will be a 3 by 3 matrix. So you make a matrix A, and the matrix B will contain these constant numbers, and A inverse multiplied by B will give you these values. T1 equal to 4.2 Newton, T2 equal to 7.3 Newton, and A equal to 0.72 meter per second squared. A very important type of problem, and I'm sure you have followed the basic logic for solving this problem. Alright, try this on your own, and that will be a very good practice for you. Another one. A unit